Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into Chapter 7 from your textbook, starting with Section 7.1. The beginning of Chapter 7 is pretty much devoted to looking at different techniques for integration. So far in our class, we've been mostly focusing throughout the course of Chapter 6 at applications of definite integrals. We've seen how to use definite integration to handle the area between two curves from both an x and y perspective. We learned how to handle volumes of solids of revolution using definite integrals. We also understood how to use definite integration to help us understand work from physics, as well as also the average value of a function. Now, though, we're going to change gears a little bit and not continue looking at applications of integration, but instead looking at some better ways to actually perform integration. From your Calc 1 classes or your Math 190 classes, you learned some basic integrals, mostly by just taking things that we knew were derivatives of other functions and reversing that. The only technique that you guys have really seen before as a major technique is what we called U substitution. And we talked a little bit about U substitution in the sort of review at the very start of our class, and of course in some of the examples we've used U substitution. Remember that U substitution was based on attempting to reverse the chain rule, and it's very useful when trying to integrate the composition of functions. So if we see a composition of functions, one function plugged into another, then oftentimes we need to use U substitution to actually perform that integral. Overall, even though U substitution is only one technique, you guys should probably be aware that integration techniques in general, what we're going to talk about in this video called integration by parts, what we'll talk about in later videos called trigonometric substitution and partial fractions, all of these are integration techniques, and integration techniques don't attempt to do the integral. Instead, they try to change the integrand. Basically, they're trying to change what you're integrating into a form that's easier to work with. So one thing to sort of keep in the back of your head as we go into these sections 7.1, 7.2, 7.3, 7.4, which are all techniques of integration, is that everything is about manipulating the integrand, what you're trying to integrate, into something that is easier to work with. For the first technique, integration by parts, as we know, integrals distribute over addition, subtraction, and constant multiplication, right? You can break up a bunch of different terms into a bunch of different integrals and work on each piece separately. However, integrals do not distribute over products of functions. So this integration by parts technique is basically going to be an attempt to help us when we have to integrate a product of two functions. And therefore, it's reasonable to sort of believe that it's going to be based on reversing the product rule for derivatives. So, to explore this before we actually just state the integration by parts technique and try some examples, let's go ahead and remind ourselves what the product rule for derivatives said. So, let's imagine we have a product of two functions, f of x and g of x, and let's remember how you actually differentiate that product. So, the product rule for derivatives says that this is equivalent to f prime of x, g of x, plus f of x, g prime of x. So in other words, the derivative of the product is equal to the product of the first function times the second, plus the first function times the derivative of the second. So this is a derivative rule. Let's see if we can sort of translate it into an integration rule. And the way we're going to do that is we're going to integrate both sides of this expression with respect to x. So if we go ahead and we do that, so we're going to integrate with respect to x, well, we get the integral of the derivative of the product, dx, is the integral of f prime g plus f of x g prime dx. Okay, so certainly if we have this identity, then we can integrate and get this identity. Okay, now let's see if we can play around with this, simplify it, just see if this tells us anything interesting. Well, this left-hand side is very interesting because it's the antiderivative of the derivative with respect to the same variable. So, fundamental theorem of calculus tells us that this side can just be rewritten as f of x, g of x. In other words, the integral of the derivative is just the original function. Technically, there could be a constant of integration, but we can just have the constant of integration on the right-hand side, so we don't even need it here. On this side, let's just go ahead and just do it one step at a time. So let's rewrite this. Okay, that's sort of a nice simplification. All right, on this right-hand side, if nothing else, we know that the integral distributes not into each product, but over that addition, so we can break it up into two separate integrals. So f of x g of x is the integral f prime g of x dx plus the integral f of x g prime of x dx. All right. So what does this sort of tell us so far here? Well, let's go ahead and sort of rearrange this a little bit. Let's go ahead and bring this piece over to the other side. It doesn't really matter which one we're going to bring, but let's go ahead and bring this guy over there. So we're going to think about that as f of x g of x minus the integral f prime times g of x dx is equal to the integral f of x g prime of x dx. And then just for simplicity, I'm just going to write this guy onto this side and these guys onto this side, just reverse it so that the single integral is on our left-hand side because we usually like to read left to right. So this is telling us that the integral of f of x g prime dx is equal to f of x g of x minus the integral f prime g of x dx. Okay, this is a good moment to say, so what? What is this actually telling us? Okay, well, it might not be too much, but actually, this shows us a integration technique. Because remember, we sort of said that an integration technique is just an attempt to change the integrand. So, imagine you have an integrand of this form, f of x times g prime dx. So in other words, you have a product of two functions. So you're trying to integrate the product of two functions. Now we're sort of imagining that one of the functions happens to be a derivative. But again, any function could potentially be the derivative of some other one. So you should really view this left-hand side as a product. So we have the integral of a product. And we're saying that it can be found as being equivalent to f of x times g of x. So this f of x function just brought directly over, and g of x, which of course would be the derivative, or sorry, the antiderivative of just the g prime, not the antiderivative of the product, since that's what we're trying to avoid, but just the antiderivative of the g prime, and then minus another integral. And you might say, well, that's not so great. That means I have another integral to do. But notice it's a different integral, and it's f prime, the derivative of what we originally had there, and g of x, the antiderivative of what we had there. So in other words, it changes the integrand from f of x g prime to f prime g. Is that guaranteed to be better? Not at all. But could it be better? It might just be. So this is the technique of integration by parts. It basically says that you can rephrase the integral of a product as this product minus an integral of a different product. And as we'll see, if you carefully choose which function to think about as f of x and which to think about as the g prime, then this resulting product might be a lot easier to work with. So this will begin to make a lot more sense once we get into some computational examples. But again, the big idea, the sort of theoretical idea I want you guys to sort of think about is that we have a product here, but we can change and integrate a different product here. And if that makes it an easier integrand, then this is a worthy technique. So let's go ahead and summarize this, and explicitly we're going to sort of rephrase it out of this function notation, because to be honest, this function notation is very messy, and there's sort of a famous way to sort of memorize this very easily. So the summary of integration by parts. So you can sort of phrase integration by parts as very, very formally as follows. So we're going to suppose we have the functions f of x and g of x, and we're going to further suppose that capital G of x is the antiderivative of little g of x. Then we're saying that the integral of f of x g of x dx, so the integral of the product, can be found by taking f of x times the antiderivative of g of x minus the integral of the antiderivative of g of x times the derivative of f of x dx. Now, this right here is very formally what integration by parts is really doing. And it's based directly on what we just did back there, just by writing g of x, capital G of x, as the antiderivative rather than just saying the antiderivative. This right here, though, is absolute garbage in terms of trying to actually remember this rule, because this is so sort of messy. So the famous way that you see this sort of written out is people sort of condense it, and it's often written in this sort of format, where we say that the integral of u dv is equal to uv minus v du. In other words, what it's saying is that the integral of this product can be thought about as integrating that dv to the v and then subtracting that integral of the dv times the derivative of that u. And this is sort of the way that you memorize what the structure is. Now, a couple little notes about this. First of all, as with almost all of the techniques of integration we're going to talk about, U substitution, integration by parts, and later ones in later sections, these techniques do not do the integral for you. Once you apply one of these techniques, you are never going to be done. That's sort of a sad way of looking at it, but you're not going to be done yet. Let's phrase it like that. After integration by parts, you now have another integral. The whole point of integration by parts is that hopefully this new integral will be easier to do, but it will never be concluded right after integration by parts. Instead, you'll always have another integral to do. Remember, the whole goal is to hopefully change the integrand into something that we know how to integrate. Now, we're about to get into our examples and actually see how to really use this rule. One thing you should keep in mind is that at the beginning of each of these examples, we're going to have a discussion about how to choose which part of the product should be considered that f of x and that g of x, or in the better way, in sort of the easier to remember way, which of them is going to be considered the u and which is going to be considered the dv. All right, let's get into those computational examples, and hopefully this will begin to make a little bit more sense. So, we're going to try to perform the following indefinite integral. So, nice sort of basic indefinite integral to begin with. This is a classic integration by parts. What are we going to try to integrate here? Well, we've got x times sine x dx. Why is this a classic integration by parts? Because we have a product. We have a product of x and sine x. We cannot just distribute the integral. We can't just say that this is going to be like 1/2 x squared and then times the integral of sine x, which is that negative cos x. Doesn't work like that. You can't distribute integrals over products. So, as far as we know, we're sort of stuck. Could we try u substitution? Sure, but there's no composition, so there's nothing really to u sub for. We can't really manipulate this algebraically, so we want to try this new technique, this integration by parts. So, for integration by parts, the best sort of way to write it up is to make a selection for your u and your dv. So, in this case, you have some options. We can put the x as u and the sine x as dv, or we could put the sine x as u and the x as dv. Now, we're always going to stick the dx onto the dv. That's just sort of notational. So we know that this one's going to have a dx there. Okay, how do we make that selection? Well, we do that by thinking ahead a little bit. In this sort of format, what we're going to do is whatever we select as the quote-unquote u, we're going to differentiate. We're going to have to calculate du, and that's going to be under differentiation. Now, differentiating things is very easy. We know that we can differentiate pretty much anything out there. However, whatever we select as the dv, we're going to have to change into v by integration. So whatever we put here, we're going to have to know how to integrate. Now, that is a much more limited set. There are a lot of things out there that we don't really know how to integrate, so any of those things would be terrible choices for dv. So we're going to think about our choice for dv first. So, in this case, we have our x and our sine x. If we put the x here, would we know how to integrate it? Yes, we should know how to integrate x dx. What if we put sine x? Do we know how to integrate sine x? Yes, we know how to integrate it. So, both of them are okay choices for dv. If one of them was something we were not comfortable with integrating, for example, if it was something like x times ln x, we don't really have a nice antiderivative for ln x, then we wouldn't want to put the ln x in the dv because the first thing we would be forced to do is try to integrate it. But in this case, both pieces are integrable. All right, then we look at this piece. Remember that what we put here, we're going to differentiate. Some things simplify a lot under differentiation. Well, if we put the x here, differentiating it is going to basically make it a 1. That's a great simplification. If we put sine x here, then differentiating it is going to become cosine x. That's not a simplification at all. We're trying to simplify our integrand, so let's choose the x here. So we'll pop the x here, and we'll make the dv sine x dx. Under differentiation, our du is going to be 1 dx. Now the dx will be on the du. And under integration, the integral of that sine of x is negative cosine x. So now we're ready to use our integration by parts. We're saying that the integral of u dv, so the integral of x sine x dx, is supposed to be equivalent to uv minus the integral v du. So let's actually put this stuff in. X sine x dx is supposed to be u times v, so u times v. So x times negative cosine x minus the integral v du. So negative cosine x times 1 dx. Okay, let's simplify this a little bit, and then we're going to take a look at this integral here and hope that it's something that is easier to do than what we originally started with. So we can say the integral of x sine x dx, it looks like negative x cosine x, and then we've got double negative, so plus the integral cosine x dx. Okay, integral cosine x dx, still an integral. Is it an integral that we know how to do? Absolutely. So we can go ahead and integrate. Integral x sine x dx is negative x cosine x plus sine x plus c. And there we go. We were able to integrate this product using integration by parts, and we got its antiderivative as this family of functions there. Now, we're going to do a bunch more examples in just a moment as we go through this to get more comfortable on the selections of u and v and u and dv and see all the things that can sort of happen there. But just for fun, and since this is our first time doing this, let's actually check that this makes sense. So in other words, I mean, we did this technique. I showed you guys where this technique comes from, but let's see if we can confirm that our solution really works. How would we confirm that the antiderivative of this is really equal to this? Well, we could always check by differentiating this and making sure we get back to what we were trying to integrate. So just for fun, for this one only, we'll go ahead and do a check. We'll differentiate our negative x cosine x plus sine x plus c. If we differentiate that, we'll have to do a product rule here. So the derivative of that negative x is going to be negative cosine x. The derivative of cosine x is negative sine x, so we get x sine x. The derivative of sine x is cosine x. And of course, the derivative of the plus c is going to be 0. Then here we have a negative cosine x and a cosine x. We can cancel those out. And we get x sine x, check. Right? The derivative of this is really x sine x, so the antiderivative of x sine x is really equivalent to that. So this shows you, at least in this example, integration by parts really does work. Okay, so let's recap real quick before we get into our examples. When we're doing this, we need to choose a u and dv. Whatever we choose for u, we're going to need to know how to differentiate. We know how to differentiate everything, so that shouldn't be a trouble. Whatever we choose for dv, we're going to have to integrate. Some things we don't know how to integrate. If there is anything in the expression, in the product that you don't know how to integrate, make sure you don't put it in for dv. If you do know how to integrate both pieces, like we did here, then you want to choose for u whatever is going to simplify the most under differentiation. In our case, the x under differentiation became a 1. Nice and simple, that's what we chose. If you're unsure, you can always do it twice. Choose one way, see what happens. If you get an integrand that's nice and easy, use it. If you don't, try the other way and try it again. There's nothing wrong with sort of some trial and error here. All right, let's take a look at our next one. We're going to try to do this indefinite integral, ln x over x to the 8 dx. Now, might not be immediately clear that it's an integration by parts because we said integration by parts is good for products, but keep in mind we can rewrite this as a product pretty easily. We can view this as x to the negative 8 ln x dx. Okay, let's try this integration by parts approach. So we need to choose a u and a dv. Whatever we choose for u, we're going to end up differentiating, and whatever we choose for dv, we're going to end up integrating. For this, we're also going to always include the dx on the dv because that makes sense for integration. Okay, two components here, x to the minus 8 and ln x. X to the minus 8 as a dv, well, integrating x to the minus 8 should be a power rule, pretty easy. ln x, integrating ln x, well, we know how to differentiate ln x, but we don't have a nice antiderivative. So we want to make sure that we don't put that one there. So that means we should put the x to the minus 8 there, and we should put the ln x sort of without choice there. Notice that avoids us needing to know how to integrate ln x. Okay, now we can proceed. Du, the derivative of ln x, that's nice and easy. That's just 1 over x dx. And the integral of x to the minus 8, well, it's going to be x to the minus 7, and then the reciprocal, so negative 1/7. All right, now our formula, integral u dv, is going to be the integral u dv is going to be uv minus the integral of v du, always going to be using that. So that tells us that the integral of x to the negative 8, ln x dx, u times v, is going to be negative 1/7 x to the negative 7 ln x minus the integral v du. So we're still going to have an integral to do, and that integral is going to be minus 1/7 x to the minus 7 times 1 over x dx. Okay, let's simplify this a little bit. We get integral x to the minus 8 ln x dx is minus 1/7 x to the minus 7 ln x. Looks like we get plus the integral of 1/7 x. This is also an x to the minus 1, so we can think about it as x to the minus 8 dx. Okay, hopefully this is an integral we know how to do. If not, we might have to try a different combination or some other technique. But of course, this is just power rule, so we're all good there. X to the minus 8 ln x dx is negative 1/7 x to the negative 7th ln x. And here, if we integrate that, we're going to get x to the minus 7th, put the reciprocal of that in front, so minus 1 over 49 x to the minus 7th plus c. Always put your plus c after you've finished all of your integration. So as soon as you do that last one there, when there are no more indefinite integrals, then you can put the plus c. So there we go. There's our integral of x to the negative 8 ln x. In terms of this, keep in mind here, we had an initial sort of modification to recognize that that quotient could be written as a product. And then once it was a product, we tried integration by parts. Here was an example where we were sort of forced into our selection of u and dv because we did not want that ln x in for dv. That's what we wanted to avoid there. Okay, let's go ahead then and take a look at some more examples. All right, we're going to try to perform this indefinite integral. Notice once again, it's almost immediately clear it's going to be integration by parts. X squared e to the x, that is a product. So we're going to try this integration by parts technique here. So integration by parts, u and dv, whatever we choose for u, we're going to need to differentiate into du, and whatever we choose for dv, we're going to have to integrate. Again, we know that the dv part is going to have the dx. Okay, so we've got two choices, x squared and e to the x. X squared is an integral, sure, know how to do that. E to the x is an integral, definitely know how to do that. So, unfortunately, the integration part doesn't tell us anything in terms of information. Over here, though, which is going to simplify? Well, if I take x squared and differentiate it, it becomes 2x. That's a little better, I suppose. And if I have e to the x and differentiate it, it stays e to the x. That doesn't help at all. So that probably tells me I'd like to put my x squared here, and I'll put my e to the x dx there. We'll see if this makes things better. Let's take a look. This will become 2x dx, and the v under integration is going to be e to the x. So that tells us the integral of u dv is equal to uv minus the integral v du. So we get the integral x squared e to the x dx, that's the integral we're trying to do, uv, so x squared e to the x, minus the integral v du, so it looks like e to the x 2x dx. Let's do a little simplification. That's x squared e to the x dx is equal to x squared e to the x minus, I suppose, the integral we could write as 2x e to the x dx. Okay, this time I'm not particularly thrilled by what I got here because it's still a product. We still have x e to the x. But the only good thing is instead of having a quadratic there, it actually has a linear term. So it got a little bit better, but it's still a product. I can't just directly integrate this. But we have this technique, integration by parts. Let's try it again. Right? If it allowed us to go from x squared down to x, now we can use it again to go from x to a constant, and then we should be able to integrate. So now we're going to take just this component here, and we're going to try integration by parts on this. So for that integration by parts, I'm going to still use the same letters, u and dv. The u now, well, same idea. We're going to have to think about the u and the dv. Whatever I choose for u, I'm going to have to differentiate into du. Whatever I choose for dv, I'm going to have to integrate. If I were to put the e to the x here and the 2x here, then all that's going to happen is I'm going to go back to where I started. So I don't want to do that. I want to stay sort of consistent here. So I'll put my 2x here, and I'll put the e to the x dx here. We know that differentiating the 2x will make things a little bit easier. It'll make it only a 2 dx, which is great. It's just a constant. And the integral of e to the x, of course, is e to the x. So now we have integral x squared e to the x dx. We still have that x squared e to the x minus, let's put a big set of parentheses because that minus is going to apply to everything here. We use this same formula, our uv, so 2x e to the x minus the integral, that v du, which is e to the x and 2 dx. So e to the x, 2 dx. Close up that big set of parentheses. Okay, let's do a little bit of simplification. We still have an integral, so we're still not quite done. X squared e to the x dx is x squared e to the x minus 2x e to the x plus the integral of 2e dx, right? That's just distributing that negative sign. All right, integral 2e to the x dx. Hopefully we know how to do that. Yep, that absolutely is. We know how to integrate e to the x dx. The 2 is just a constant, so we can stick it outside. And we can get that the integral x squared e to the x dx is x squared e to the x minus 2x e to the x plus 2e to the x. We finished all our integrals, so we can put our plus c there. So there we go. So this is an example for you guys of using integration by parts twice. What would have happened had we had x cubed e to the x? Well, then we would have had a very messy needing to use integration by parts 3 times to go through and do it. But notice that the integration by parts each time, because we differentiated the polynomial piece, that x squared, reduced in order, went from x squared to x, and then from x down to the constant. And then we were able to just do the antiderivative. So integration by parts sometimes can be used several times to reduce the order of a polynomial piece like that x squared. All right, let's take a look at another example that sort of mixes some of the techniques that we've learned together. You guys have already seen u substitution. Now we have this integration by parts. They can be used together. Let's go ahead and try to perform this indefinite integral. We've got x to the 9th cosine x to the 5th dx. Now, we should immediately see that there is a product here of 2 functions, so we're thinking integration by parts. But before we can even do that, we should notice that we've got this cosine x to the 5th, and that is a composition. So before we do anything else, if we're going to have to work with this cosine x to the 5th, since it is a composition, we're going to have to begin with a u substitution. We really don't want to have to carry that composition throughout the entire thing. So let's start by doing this as a u substitution. Let's get rid of that x to the 5th there. So our du then is going to be 5x to the 4th dx. We don't see an x to the 4th anywhere in there, so it's probably best to just go ahead and solve that out. 1 over 5x to the 4th du is going to be equal to dx. We can then plug this stuff in, and it'll be a little bit messy, but we've got this x to the 9th, then cosine u, and then 1 over 5x to the 4th du. Now, this is not a particularly great form because we actually have 2 variables in here, x and u. We can only have the variable u now before we can proceed. This is sometimes referenced as an imperfect substitution, so we need to go ahead and figure out a way to remove all of the x's in this expression before we can go ahead and finish up integrating. So luckily there's a pretty easy simplification at the beginning. We can cancel the x to the 4th and the x to the 9th and make this a 1/5 x to the 5th cosine u du. Still not great though, because we have x to the 5th and u, so we have 2 different variables. But luckily that x to the 5th is exactly our substitution, so we can replace it with 1/5 u cosine u du. And now we can proceed from here. And that's because everything now is in our new variable u. This, unfortunately, we can't just integrate directly. It is still a product, so we will need to go ahead and use integration by parts from here. So notice that we did our U substitution first, and then it led to a simpler product, a product without a composition, and then we're using integration by parts. All right, so our U is already sort of used as a variable, so we'll do this as W and dV. Remember that whatever we choose for this W, we're going to have to differentiate and make into dW. And whatever we choose for dV, we're going to have to integrate into V. And of course, whatever we choose for dV is going to have that du attached to it. So we could take the 1/5 and stick it outside, or we can just carry it along. Doesn't matter as long as we account for it in some way. I'll just carry it along as a 1/5 U and a cosine U. So in terms of integration, we could certainly put 1/5 U here and integrate that. We should know how to do that. We should also certainly know how to integrate cosine U. So either thing could go here. So we'll turn our attention to what maybe is going to simplify the most under differentiation. If we put the 1/5 U here, differentiating that is just going to become a 1/5. That is a constant. That's nice and simple. That sounds like the way we want to approach this. So we'll put the 1/5 U here, and we'll put the cosine U du here. Differentiating that 1/5 U is going to give us a 1/5 du. And integrating that cosine U is going to give us a sine of U. So we then should have our WV, so that'll be 1/5 U sine U minus the integral of that V dW, which is going to be 1/5 sine U du. As always, the integration by parts still results in another integral, but it is a simpler integral because it's just a constant in sine of U. We know how to integrate a sine of U, so we can go ahead and do that. 1/5 U sine U. Integral of sine of U is cosine of U, so we get minus 1/5 cosine U. No, integral of sine of U, sorry, is negative cosine U. There we go. So we get plus 1/5 cosine U there. And then we get our constant of integration plus C. So there we go. We've got our expression there. Of course, it can't be our final answer because it doesn't make sense that this is in terms of U. So we can go ahead and replace U with x to the 5th. So we get 1/5 x to the 5th sine of x to the 5th plus 1/5 cosine of x to the 5th plus C there. So there we go. We've got our antiderivative of this function using both a U substitution and an integration by parts. Notice that basically the idea here was that the composition was the first thing that we noticed, so we made sure to take care of that with U substitution. Even after the U substitution, even though that ate up a lot of the x to the 9th because x to the 4th was used up in the substitution, we still had a U left over, so we still had a product of two functions, so that's why we were forced to still use integration by parts there. All right, let's look at just a couple more basic examples here, specifically of some more interesting ways that integration by parts can be used. So far, all of the examples we've done have always been in sort of obvious product, which is why we picked integration by parts. I want you guys to see a couple other ways that it can be used. So we're going to actually take the antiderivative of a function that we mentioned at the very start that we don't have an easy antiderivative of. We're going to actually see how you can determine the indefinite integral of ln x dx. Now, this doesn't immediately resemble an integration by parts, but we are going to try the technique for this. So, integration by parts here, we're going to try to choose a u and dv. Well, there's not much choice here because we're trying to avoid having to directly integrate that ln x. So we're going to put the ln x here, and we're going to just put the dx here. So this is a little bit of a trick with integration by parts. Sometimes if you just see a single function, you can think about it as a product of that function and 1. And that's what we're doing here. So differentiating, we're going to get 1 over x dx here. And integrating this, we're going to get x. So we can then say that the integral of ln x dx, well, it's going to be that uv. So we get x ln x minus the integral of that v du. So x 1 over x dx. We can simplify, and we get the integral ln x dx is x ln x minus the integral of 1 dx. And that is a nice simple integral to do. We get integral ln x dx is equal to x ln x minus x. We've completed all our integrals, so we can put our plus c. And there we go. Now we've completed something we actually set out at the very beginning of our class. We said ln x is a basic function that we don't have an antiderivative for. Well, now we do. We know that the integral of ln x is x ln x minus x plus c. So this is a sort of just a little example to make you guys recognize that in the majority of cases, integration by parts is very useful when you have a product, but there are some other applications for it. Sometimes you can take a single function, treat that single function as a product of that function with one, and try integration by parts. Let's try that once more, but in a situation with a definite integral, just to make sure we're comfortable with that as well. We're going to try to integrate 0 to 1 of another sort of basic function that we don't already know the antiderivative of, arctangent of x. So let's do our same sort of trick. We're going to try integration by parts. We're going to let u be arctan x, and we're going to let the dv just be the dx. So again, we're sort of using a 1 dx times the arctangent. So if we do the derivative here, we'll get 1 over 1 plus x squared dx. And of course, when we integrate this, we will get x. So we will then get that the integral from 0 to 1 arctangent x dx is equal to, well, v times u, or u times v, so x arctangent x minus the integral of this v du, so minus x over 1 plus x squared dx. Now, we're going to put all of this in sort of some brackets and put an evaluation bar from 0 to 1, because we're going to have to evaluate this entire thing at 1 and then subtract what happens at 0. But we should do that evaluation after we finished integrating here. So to perform this integral, now we got to think about this. This is still relatively complicated. It's still a quotient or a product, right? So we got to think a little bit here. But notice that down here, the derivative of 1 plus x squared is 2x, which we have something resembling that here. So we can actually do this as a u substitution. So we're going to do a u sub here, with u being 1 plus x squared, and our du being 2x dx. We don't quite have 2x dx, we have x dx. So we can think about this as 1/2 du is x dx. So we'll go ahead and pull this stuff over to here. So we have our x arctan x minus the integral. This x dx is just going to become a 1/2 du, and then of course our denominator is going to become u. So we have 1/2 over u du evaluated from 0 to 1. And of course this evaluation 0 to 1 applies to x, so we'll have to finish this, undo our substitution, and then plug in. You might say, why don't we change the bounds? Well, we could change the bounds, but those changed bounds would only apply to this. They wouldn't apply to this piece here. So it's probably easier to do all this, undo the substitution, and then plug in the original bounds. So we get x arctan x, looks like minus 1/2 ln absolute value u. And that's evaluated from 0 to 1. We can plug back in, that's x arctan x minus 1/2 ln, and then our u was 1 plus x squared, evaluated from 0 to 1. You'll notice that right here I'm dropping the absolute value bars because 1 plus x squared is always guaranteed to be a positive number, because x squared is always positive, plus 1 is going to make it certainly positive, so I don't really need those absolute value bars. Now I can go ahead and plug in. I plug in 1 here, so it looks like I get arctan of 1 minus 1/2 ln of 2. And then subtract, we plug in 0. So it looks like 0 minus 1/2 ln of 1. So it looks like that is going to become, well, arctan of 1. What angle gives us a tangent of 1? That would be pi over 4 minus 1/2 ln of 2. This is 0. Ln of 1 is 0, so that's all 0. There we go. So not only did we figure out the antiderivative of arctangent of x, we actually did that along the way. We figured it out right here. The antiderivative of arctan of x is x arctan minus 1/2 ln 1 plus x squared. But we also evaluated it from 0 to 1 and got this value. Okay, let's wrap up this introduction into integration by parts by taking a look at probably the most sort of unique and strange situation that integration by parts can be used on. So let's go ahead and take a look. We're going to try to perform this indefinite integral, the integral of e to the 2x sine x. Now, initially, this should look very similar to everything we've been doing because it is a product. So let's go ahead and try to do our integration by parts here. So we're going to have to choose a u and dv, and of course the dv is going to get the dx here. So in terms of which of these we can integrate, we can certainly put the e to the 2x here. We know how to integrate that. And we certainly also know how to integrate sine x. So either one could go there. In terms of what might simplify under differentiation, well, if we differentiate e to the 2x, it's going to become like 2e to the 2x. So that's not going to really simplify much. And if we put sine x, well, when we differentiate, that's just going to become cosine x. That doesn't seem to simplify much. So it doesn't really necessarily seem like there's a great choice. So let's just pick one and see what happens. So I'm going to go ahead and put the e to the 2x here so that we can differentiate a little bit more easily. And then we'll put the sine x here. If we did choose to put the e to the 2x there, it wouldn't be that bad, but then every time you integrate, you'd have to get a factor of 1/2 because you'd be technically doing a u substitution because of that 2x there. For now, though, we'll go ahead and get our du, which will be 2e to the 2x, and our v, which is integrating that sine x, which would be negative cosine x. So we could then say that the integral e to the 2x sine x dx is equal to that u times v, so it looks like we get negative e to the 2x cosine x minus the integral of that v du. So we'd get, looks like, oh, and we should have our dx there, excuse me. So we should get minus 2e to the 2x cosine x dx. Okay. Now, we can simplify this a little bit, and it looks like we have that the integral of e to the 2x sine x dx is negative e to the 2x cosine x plus the integral 2e to the 2x cosine x dx. Now, if we cross-compare, this is the integral we were originally trying to do. Now this is the integral we're trying to do. This doesn't look much better. But, of course, we've run into situations before where it took more than one integration by parts. So let's try integration by parts again here. So we're going to try integration by parts on this piece. So let's let our u be the same structure. We'll just carry the 2 along with it. So we'll do 2e to the 2x. And we'll let the dv be that cosine x dx. Obviously, I wouldn't want to switch their positions because if I did, I would just get back to where I started. So since I chose this structure initially, I'm going to try to stay consistent with that. The du then would be 4e to the 2x, so it doesn't look much better. And the v here, integral of cosine x, is going to be sine x. So we pop that stuff in there. Integral e to the 2x sine x dx is negative e 2x cosine x. We still get that. Now we do our u and v. So it looks like plus 2e to the 2x sine x. And then minus the integral. And we get our v du. And again, sorry, I keep reading the dx there, but there we go. V du. That looks like we get 4e to the 2x sine x dx. Okay. This doesn't look much better because, again, now we still got that product of e and sine. So it seems like we're just going around in circles. And in fact, we actually are going around in circles. If you look at this right here is exactly that product. Let's actually see if we can explore that a little bit. Let's pull this 4 out front. We get the integral e to the 2x sine x dx is negative e to the 2x cosine x plus 2e to the 2x sine x minus 4 times the integral e to the 2x sine x dx. And it's very interesting that this is exactly the integrand that we started with. And notice that nothing else involves an integral. So what happens if instead of trying to solve for this integral manually, what if we just bring this over to the other side? We add 4 times the integral e to the 2x sine x dx on both sides. Well, if we do that, on this side we get 5 times the integral e2x sine x dx. And then on this side, we'd have this expression, which notice doesn't involve any integrals anymore. So we can actually just divide both sides by 5 and get our antiderivative. We can see that the integral of e to the 2x sine x dx is actually negative 1/5 e to the 2x cosine x plus 2/5 e to the 2x sine x. And there we go. We came up with our antiderivative. Now we know we've finished our integral, so at the very end here, we can pop on our plus c. And this actually allowed us to find this antiderivative without ever actually needing to integrate. Instead, we used integration by parts twice, ended up at this exact same integrand, and then solved for our antiderivative algebraically. Now, this is not a common thing that happens, but it can happen when you have these what we call sort of cyclic functions. And the whole thing is that the sort of derivative of sine and cosine keeps flipping back and forth. And then, of course, every time we worked with that e to the 2x, it just always remained as an e to the 2x. So this is not something you're going to see a ton of, but if you ever see products of like an exponential and a sine and cosine, you should be a little bit suspicious that you might have to do this pair of integration by parts and then solve algebraically here. Just wanted you guys to see at least one example of that. For now, though, this is going to wrap up our introduction into section 7.1, your first new technique of integration by parts. In our next video, we'll be moving on into section 7.2 and taking a look at how to deal with some trigonometric integrals.